Well, greetings, mathletes, and welcome back. We're going to be taking a look at graphing polynomials this time. So last time we looked at graphing quadratics. This time we're generalizing that whole business to polynomials in general. Now, what's kind of nice about this is that there's actually very little computation that goes on. You may have to factor something, right? You also may not have to factor something. That's about the worst thing that you'll need to do. But we do need to be aware of some properties so that we can use them, so that when we see the equation of a polynomial, of a polynomial function, we know what pieces to pick out, so we can figure out what the shape of the graph is. Okay, so let's go ahead and get started here. Okay, so first off, I think most of us probably know what polynomials look like, right? We could pick one out if we see one. But I'm going to give a more, I'm going to show the general way to present it. So if we have a function, and a lot of the time when you have a polynomial function, you use P, Q, and R for the function names. But you still might see F, G, and H. But in any case, if we have a polynomial function of x, we can organize it this way, where we have an x to the n plus a n minus 1 x to the n minus 1 plus, and that's just going to keep on going. So that exponent gets smaller and smaller until we get all the way down to a1 x to the first power plus a naught x to the 0. Okay, now remember, x to the 0 is equal to 1, right? And so if it's equal to 1, really, I don't have to write it. It's kind of there for theoretical purposes so that we can see all of the exponents represented in this thing. Now, parts of this that are of interest. This right here is called the leading term. That's the leading term because it has the highest exponent on a variable. Okay? an, actually I should do it this way. An to the x to the n is the leading term. An is the leading coefficient. Oops, that didn't switch over. Let's try and do that. An is the leading coefficient. And n, right, that exponent right there, and it's always the biggest exponent you have in your polynomial. N is the degree of the polynomial. So this is an nth degree polynomial. And we use nth degree just because it's general. We can talk about all kinds of stuff. Now, one of the things that's really nice about this you can actually tell a lot from this leading term. The exponent tells you something, and the leading coefficient tells you something. And so we're going to take a little look. I have a little demonstration here so we can kind of get an idea of what's going on. So let me switch over here. All right, so let's take a look at this. Okay, so what the heck is that? Okay, in any case, so this is the graph of g of x equals x. So I want to point some things out about this. One, if it's g of x equals x, then that means it is, let's see if I can do this without it disappear. Oh, it's going to disappear either way. If g of x equals x, what that means is that an x to the n is equal to just x, which tells me that this is a1. A1 happens to be equal to 1 because that's my coefficient here, and the exponent is n. So this is a first degree polynomial, right? Notice what it does. It goes straight through the origin at a 45-degree angle. The thing we're going to end up noting is just what the ends do, like what it does out. Oh, I can't do that. Okay. What it does on the outsides of the function, right? What the tails do. So let's just up the exponent here and see what happens. Okay, so let's do that. And then let's take g of x. And this time we're going to square it. Okay, so now let's see what happens. Okay, we get what we expected. This is a parabola, right? So notice both ends are going up. The last time when the exponent was 1, the ends go opposite direction. One went in the negative direction, one went in the positive direction. Okay, so now that we've made it an even exponent, it's an even degreed function, both ends go the same direction again. So, oh, there it is. So let's change the exponent again. Let's change it to a 3 and see what happens. Oh, now they go opposite directions again. So now I have an odd exponent again. I have x to the third, right? Right, that's my function up here. Yeah, and they go opposite directions. So that's kind of interesting. Let's go ahead and change it one more time. Let's see what happens when it goes to the 4th power. Okay, now that we're at the 4th power, they're both going the same direction again. That's kind of interesting. It turns out it has to do with whether the exponent is even or odd. If I pick an odd exponent, right, like if I pick 7, 7's odd. That means that the two ends should go opposite directions. And again, they do. And you notice this still looks a lot like x to the third, doesn't it? Right? If I looked at x to the third, it does the same thing. The difference is this middle piece down in here from -1 to 1, that piece starts to hug the x-axis a little closer, and the other sides get steeper as the exponent goes up. So if I pick something like 17, it would still look pretty much the same, but the middle part would be a lot flatter, right? You see how much flatter it is? Now, the same thing happens with even exponents, except both endpoints keep going the same direction. So we saw squared, right? If I make this a 4th power, it should look a lot like the square, but the bottom will be flatter, right? You see, it's a little bit flatter. If I start making a bigger even number, like let's say I pick 18, let's see how close it hugs the x-axis now. Yeah, see, it flattened it out pretty good when I made it an 18. So, what I want you to take from this, as we go through this, is that if the degree is even, the endpoints go opposite direction, or excuse me, the endpoints go the same direction. They'll either both go up, or they will both point down. One of the two, right? Okay, so that's what happens there. Now, if the degree is odd, right? If degree, oh, still got to have the pen active. If the degree is odd, what that means is they go opposite directions. So you may have one that does this. Now, keep in mind, what happens in the middle could be a lot of different things. The examples we saw just flattened out in the middle like that because of the fact that there were no other terms in that polynomial. If I started adding things to it, you'd start getting all kinds of wavy things going on, but the ends would still do the same thing, and that's what's important. Right, so we'd have things going opposite direction if the degree is odd. Also, you could have it going this way, right? One side could go up this way and the other side could go down, right? And again, anything could happen in between. I just want to point that out. We're only looking at what happens with the ends. Okay, so now there's something else, and we are going to formalize all this here in a second. I want to take a look at this demonstration again. Let's see what happens when we start messing around with this stuff. I am going to just switch it down to a more bite-sized exponent. I'm just going to pick x squared because we know the ends act the same. I'm not really concerned with what's happening in the middle. Okay, so we're back here. Now, if we think about what we learned about graphing parabolas, if I put a negative number out front, that will make both ends point down, right? So if I just put like a negative 2 out front and hit OK, it turns it downward. And now both ends are still going the same direction, but they're going down. Same thing happens with x cubed, right? And all the things that have odd exponents, they all do the same thing. So if I look at x cubed, it has that jig jog right there. But if I throw a negative in front of it, like if I throw a -2 on this, what it'll do is it flips it end for end. So now it goes down to the left and up to the right. Now, after I've changed it, it goes up to the left and down to the right. So it just flipped it end for end, is what it actually did. So let's see if we can formalize what all this stuff means. And I'm actually going to go ahead and let's do this. I'm going to get all this stuff down. That's just vocabulary. And we're going to organize this a little bit better. Okay, so this all has to do with the leading coefficient. And so sometimes this is called the leading coefficient test. It's not really a test as much as, just taking a look at it and see what you need to do. Okay, so this all has to do with this, with a to the n, or a sub n, x to the n. Okay, so if, let's do it this way. We'll do it n is even and n is odd. I'm just going to put this together in a little table so we can see what's going on. An is positive or an is negative. And so again, we're only caring about what the ends do. We're not caring about how much the middle wiggles. So if n is even, we know both ends go the same direction, right? So if the leading coefficient is bigger than 0, both ends go up, right? And it could do anything in between. If if your leading coefficient is negative, then we know both endpoints go down. And again, it could be doing anything in between these, right? Okay, so those two cases. Again, we only care about what the ends are doing right now. Now, if n is odd, well, if the leading coefficient is positive, it goes up to the right, down to the left. And again, it could be doing anything in between here. Right? They could go all over the place. If the leading coefficient is negative, this swaps. Right? And so it just switches the orientation of what's going on. And so that's where we start. Okay? Now, from here, if we know where the ends are, we know which direction we're coming in if we do something like, find something like an x-intercept or things like that. We can actually, we'll know if we're coming into the x-intercept from above or if we're coming in from below. And yeah, so it's kind of fun that way. So this is the first piece. Okay, so let's go ahead and clear this off. Okay, now we talked about the odd and the evenness of the power. Okay, but there's also an odd and evenness to the function. Yeah, functions are either odd, they're even, or they're neither. What's nice about knowing whether a function is odd or even is it tells us something about the symmetry of the graph. So this actually comes up in trig because sine and cosine happen to be odd and even functions. So, well, with polynomials, there's actually a really simple way to tell whether you're dealing with an odd or an even function. But I'm going to start with the definitions, and then I'll tell you how to tell with polynomials. So even functions is actually easier to tell. right? Even functions basically have this property that if I stick a negative x in for x, right? So I substitute negative x in for x. This is the same thing as what you started with, right? So here's a good example. F of x is equal to x squared, right? If I take and substitute in a negative x, so f of negative x is equal to negative x squared. Well, what happens to that negative? If I'm squaring a negative, it turns it positive. And so this ends up being x squared, which is still my original function. So x squared is an even function. The classic example from trig is the cosine function. Because cosine is an even function, it has the property that cosine of negative x is the same thing as cosine of x. And that's actually quite useful to use because a lot of the time you'll substitute in a negative x, but it's way easier to just deal with x by itself. And this will come up at some point because we are going to be covering trig. So keep that in mind. Cosine is an even function. A function is odd if, when I stick in negative x, it's the exact same thing as just taking the original function and multiplying it by a negative, right? So polynomial example would be x cubed, right? If I take f of x to equal x cubed, well, let's see what happens when I stick in negative x. So that makes it, let's see here, that's negative x, and I'm going to cube this. Well, I can treat this like a negative 1. And if I think about that, if I multiply a negative times a negative times a negative, so I'm doing it 3 times instead of 2, I get a negative back. So this ends up being negative x cubed, which is the negative of that function. This is the negative x cubed is the same thing as negative f of x, right? So this is an odd function. The trig example of that is sine. Sine has the property that if I take sine of negative x, it's the same thing as the negative sine of x. So I can actually pull a negative through the function, right? So it's actually quite useful to have an odd function because pulling a negative through it oftentimes makes life easier because, well, quite honestly, this is often a pain to deal with, and this isn't. So that's really the bottom line. Okay, now that's the formal definitions. So let me get this some of these examples off of here, and then oops. Do that. There we go. All right. Now, how to tell if something is an odd or an even function. Now, since right now we're only dealing with polynomials, I'm just going to worry about how to tell if a polynomial is an odd or an even function. You could plug negative x in and check to see, well, do I get the opposite of the function or do I get the function back, right? And if it does neither of those, then neither of these properties hold true. But for polynomials, a function is even if all of its exponents are even. It's actually why they call them even and odd functions. Later on, those of you who are climbing the ladder up to calculus, in the second semester, you actually get to see that things like sine and cosine can be represented as polynomials. They happen to be infinite polynomials, but even then, you look at the polynomial representation of cosine and all of the exponents are even. If you look at the polynomial representation of sine, all of its exponents are odd. And and I didn't write it down yet, but a function is odd if all of its exponents are odd. Eesh, boy, that E is bothering me. There. Right? So basically, you can look down the polynomial. If you have a mixture of even and odd exponents on your x's, then it's neither. Okay? If all of the exponents are even, then it's an even function. If all of its exponents are odd, then it's an odd function. Now, even functions I'll just leave the abbreviation, even fun. Even functions have y-axis symmetry. So if all of the exponents on your function are even, then your function has y-axis symmetry, right? And for odd, they all have origin symmetry, right? Now, you need to know what those things mean. Okay, so let's take a look at what that actually means. Okay, so y-axis symmetry is folding symmetry. Basically, if you fold the function on the y-axis, then both sides will match up, right? Perfect example of this is x squared, right? And all even functions have this property. If the exponent's higher, and you end up with more roots or something like that, whatever it does on the right-hand side, it also does on the left-hand side. So you only have to do one side and then mirror it. Right, so x squared is an even function. We've already established that. But we can see that it has y-axis symmetry, right? Because everything is evenly spaced on both sides of the y-axis. X cubed, which I have always thought if I was going to be a rapper, that would be my name. That'd be X cubed. I kind of messed around with, thought maybe Math Daddy or something, Slope Dog. I don't know. Anyways, let's get back to this. X cubed. That looks something like this. And this has origin symmetry. Sometimes it's called original symmetry. But the idea is if you rotate it 180 degrees, right? If you turn it 180 degrees on the origin, right? It has to, the spinning point has to be right there at 0, 0. If that's the case, then you can rotate this thing 180 degrees and get the same function back each time. So that is what original symmetry means, or origin symmetry. I don't think your book calls it original symmetry. They just say origin, but just know some books do call it original. It's not because it's the first. Okay, so that's what those two things mean. And so you notice a lot of what we're doing right now is we're trying to understand the geometry of the graph from what's in the function equation, right? Whatever defines the function. Okay, so the last thing we need to get a hold of here before we put all of this stuff together, because we've looked at a lot of little geometric things here. The last thing we need to take a look at is how the function crosses the x-axis. Okay, so it may cross it in different ways. Now keep in mind that wherever it crosses the x-axis, that's an x-intercept. So we're dealing with x-intercepts here. Y-intercepts can still be found by plugging in 0 for x every single time. And if your function's multiplied out, it's just the last coefficient. But the x-intercepts are the things that we need to take a look at. Now, x-intercepts in general, most of the time you find them by factoring, right? And if I have an x-intercept at c, right? If I have an intercept at c, then what that means is x minus c is a factor. Okay, so the factors are going to tell us how they cross. It's going to tell us where they cross the x-axis, but the exponent on our factor is going to tell us how it crosses the x-axis. Okay, so now keep in mind c is just a number, right? So if it crosses the x-axis at 2, then x minus 2 is a factor. If it crosses at -3, then x plus 3 is a factor. So it's all the same stuff you did by solving by factoring before. But we see different things happen. For example, with when I have x squared, right, when I graph that, or any of its derivatives, this is one of those things where it has an x-intercept right there at 0, right? But it doesn't go through the x-axis. It bounces off of it, right? It hits that root and then turns around and comes up. X cubed, on the other hand, has an x-intercept, and it kind of wiggles as it goes through, right? It does a little jig jog. And then x, and this is the last one that I'm really concerned with, is x by itself. It is an odd exponent because it's x to the first. So it does go through like x cubed does, but it doesn't have the jig jog, right? If it's an x to the first, it's a straight line. Okay, so these are the three graphs I want you to keep in mind. And instead of 2 and 3 here, what I want you to think about is even and odd. Okay, so if the exponent is even, it's going to bounce off the x-axis. If the exponent is odd and it's bigger than 1, it's going to do a jig jog. If the exponent's odd and it's a 1, then it just blasts straight through without a jig jog. So these are the three graphs that are going to define everything. So let's see if we can put all this together here. So let me go ahead and clean that off. Okay, so let's see if we can actually apply some of this stuff. So let's say you're walking down a dark alley and someone jumps out from behind a dumpster and hands you this polynomial. Oh, that's supposed to be a +2. And then x minus 2 cubed. There we go. Okay, yeah, and it's not multiplied out. I took the liberty of factoring it for us ahead of time so we wouldn't have to go through that right now. But this is, let's say this is what we get when we have it factored. Okay, so we're going to need to graph this thing. So there's a few things we need to get a hold of. First off, the leading coefficient. Actually, let's just look at the leading term. That's actually what I meant. The leading term, right? So that means that and we're going to do this without multiplying out the whole thing. You would, if you wanted the entire polynomial term by term, you would have to multiply this out. So that means you would square the x plus 2, cube the x minus 2, and then multiply everybody out, distribute the whole thing. And it's actually quite painful. If you want the leading term from a factored form, what you do is you take the leading term from each factor, right? So I have x, that's that one. And then that one is also an x, and that one is also an x. And then you apply their exponents. This one has a 1 on it, so that'll be a 1. This one will be a 2. This one will be a 3. So again, I'm grabbing these things. And notice I'm forgetting the root at the moment. Okay, and then you just multiply them together. Right, so normally if you have an a, it would be out front here. This example does not have that. So a is 1 in this case. So this ends up being x to the 6th or 1x to the 6th. So let's see if we can piece together the rest of the graph now. So let's see here. Let's do this. Okay, so I know a few things. I can actually look at these three factors here, here, and here, and I can figure out what the x-intercepts are, what the roots are, by setting each one of them separately equal to 0. Now, you're going to be able to do this in your head most of the time. But if you really have to, it would look like this. X equals 0, x plus 2 equals 0, and x minus 2 equals 0. And then you would solve each one. That one's already solved. This one gives me x equals -2, and this is +2, right? But again, you should be able to look at the factors individually and just see it. But if you have to, sometimes they do get a little crazy because you end up with 1/2 x plus 3/4 or something. Excuse me. Nonetheless, that means we have 0, -2. So we have one there at -2, and then one at +2. Okay, so I have 3 different roots here. Now, that means that it either crosses or bounces off the x-axis at each one of these spots. So we need to figure out what type of crossing each one makes. So to start out with, the leading term is this. Okay, so that exponent is even, which means that my end behavior is out here somewhere, right? That means they're both going the same direction. This number is positive, so that means they're both going up. So that gives me a starting point. So first off, let's look at our first root, right? Oh, that's a 0. So the first one actually would be at -2. So that gives me the x plus 2. X plus 2 is squared, which means at the root, it's going to behave like a parabola. So it's going to do this. It's going to bounce off, right? So it's going to go this way, off into infinity. But here, it bounces up. Now, it's possible you have to get an exact turnaround point or a better estimate, you may have to plug -1 into this function to see what you get. But let's take a look here. So it goes up. I know it has to come back down, and then it's going to hit 0 right here. So the factor x is the one that gave me 0, and that has an exponent of 1. So when it crosses the x-axis, it's going to behave like a line. So it's going to do this. It's just going to blast straight through it. No problem. Ooh, well, let's pretend it hit it. Okay. Now, it's got to turn around here, and then it's going to go through 2. Now, let's see what, x minus 2 is what gave me the 2, and that factor has an exponent of 3. So what we say, and just so we have the nomenclature down, this refers to the multiplicity of a root, is how many times it shows up in the factorization. So like that x minus 2 shows up 3 times, so the root 2 has a multiplicity of 3. Now, it's a cube, so that means it's going to make a jig-jog. It's an odd exponent, and it's not a 1, so that means it's going to do something like this. Right? So this function ends up looking something like this. Now, it would be really nice to have a better idea of these, because I don't know if it just humps out right here, or if it jumps way up here to like 5,000 and then screams back down and does this. I have no idea of the height here. And so sometimes you have to get kind of a good idea of what the height looks like so that you can work out the rest of the function. So if you need any extra points, what you do is you just plug them in to find out. You pick something convenient, and then you do it. So I'm going to move this because we don't know where this goes yet. And I'm going to figure out what happens at -1. So that's what I'm going to do. I'm going to deal right there at -1. So let's look at f of -1. F of -1 would be -1 times 1, 1 squared. Sorry, I'm just plugging this in and doing the math as I go. -1 minus 2 is -3, and that's cubed. So let's see here. So this is that. Basically, that goes away. That's just a negative. This is going to be -27. And negative, negative, that makes it 27. So that does blast way up there. So this thing goes way up there, and then it comes right back down. There's a turnaround point way up here at 27. So you can see how difficult some of these things get to graph. Notice I didn't put any tick marks on the y-axis just because of that. And then the same thing here. If I wanted to figure out what happens here, I would plug in a 1. And if I plug in a 1, I get negative 27. Yeah, so that would be 1. Oh no, it's not. Let me work that out. Okay. So it'd be 1 times 3 squared times negative 1 cubed. Okay, so this gives me 9. That one makes it a negative 1, so I get negative 9. So that's actually not nearly as bad as the 27, but we get the idea. This thing will go down to 9 and turn around before it does all that. So these things do get kind of hairy. And because of the extreme values, sometimes it makes it very difficult to pick the correct graph from graphing it on your calculator, because your calculator keeps the aspect ratio square for the most part. All right. Now, let's see here. See, yeah, we got this thing graphed. Okay, so I want to look at another example that might actually take a little bit more doing. And this one, I'm going to pull directly out of, where'd it go? This. Okay, so we're going to look at this, and actually I am going to, oh, that's not what I meant to do. Let me pause this and regroup. All right, so the function we're looking at here is going to be, oh, that's not what I wanted. Where's my pens? There we go. That's what I wanted. Okay. So the function we're dealing with here is f of x is x to the third minus 3x squared minus x plus 3. Okay, and we want to graph this thing. So I'm just going to walk through the questions that the homework is asking me as they're asking me them, and I'm going to work out what I can over here. So let's do this. Make it a little bit bigger. Nope. Okay. Do that, and there we go. Okay. So the first question it's asking is, we're going to use the leading coefficient test to see what this thing is doing. So this one is already multiplied out for us, so all we have to do is look at the leading coefficient. So I'm just kind of sketching stuff. Leading coefficient is x cubed, right? And x cubed has a 1, so that's a positive number, which means my end run behavior is going to go opposite directions, right? So that's what I'm looking at first. That's the first thing. And if it's down in the third quadrant like this, and it's heading south from there, that means on the left it's going down, and on the right it's going up. So let's see here. It falls to the left and right. Oh, it's the first choice. Okay. Let's see if I'm right. Hey, I got it right. Okay, good job. Way to go, Mr. Bryan. Okay, so that's the first part. Now we have to find the x-intercepts. Okay, to find the x-intercepts, we have to factor this thing. So I'm going to kind of scoot this over to factor it. And then I'll swing back after we do it. So again, we got x cubed minus 3x squared minus x plus 3. Okay, so let's see here. 4 terms, that suggests grouping. So I'm going to at least try it. So I'm going to split. Let's see here. I have x common in the, or x squared common in the front. That leaves me with an x minus 3. Back here, well, that's a negative, so I'll pull out a negative 1. and that gives me x minus 3. And so now x minus 3 is my common factor. I got x minus 3. That leaves me with x squared minus 1. See, x minus 3 is done because it's linear. That exponent's a 1. But x squared minus 1 is the difference of squares. So that means I have my x minus 3 here, and then this can be factored as x minus 1 times x plus 1. Okay, so I have 3 factors, which means I have 3 roots. That means x is equal to, let's see, the opposite of this, that'll be 3. That'll be 1, and then that one will give me negative 1. So I have 3 roots here. Now, I have a bit of a bone to pick with my math lab because it's asking for the x-intercepts. It should be asking for roots, not x-intercepts. The roots are the x values. The x-intercepts are coordinates, but all it wants here are your actual values. So you would plug in 3, 1, and negative 1. And we got that right. Okay, good. So far, so good. So we need to know which ones of these it crosses the x-axis. So let's go back to our factoring over here. Right, I'm looking at this. All 3 of these factors have exponents of 1. And so that means that they're all odd exponents, and that means they all go straight through the x-axis. None of them bounce off. You would need an even exponent to have it bounce off. So when it's asking which of the roots cross the x-axis, the answer is all of them. So 3, 1, negative 1. Check answer. Boom. I'm pretty good at this. Okay. Now, it's asking, the second thing it's asking now is at which points on the graph does the x-axis, does it hit the x-axis and turn around? Well, we already know that it goes through the axis for all of these roots. So that means none, right? It's not going to bounce off the x-axis at all. So that means there are no x-intercepts where the graph touches and turns around. Perfect. Now, the y-intercept. Well, the y-intercept is actually really nice to find. If you're given a list of factors like this, right, what you do is you make x 0 and you multiply all the numbers that are left, right? So it really is just, f of 0 gives you y-intercept. But if you have this original function here, right, the x cubed minus 3x squared minus x plus 3, if it's already multiplied out for you, oh, that's not going to work for me. Let's do that. Okay. That last number there is your y-intercept. And once again, I'm very disappointed in my math lab for not insisting that the y-intercept is an actual point instead of just being a number value. But nonetheless, plus 3, is that a plus? Nope, that's not plus. There it is. Positive 3 is in fact your y-intercept. Sorry, I got a little distracted there. Okay, so we got all this stuff now. Now they're asking about symmetry. Now remember, if it has y-axis symmetry, it's because it's an even function. If it has origin symmetry, it's because it's an odd function. And if it doesn't have either, if it's not an even or an odd function, then it has neither symmetry. So origin symmetry. Well, we have a good start here. The leading exponent's a 3, but they would all have to be odd. I would have to have exponents that are 3, 5, all that kind of stuff. And I don't have that. So, in any case, because I have a mixture of even and odd exponents, this one is neither. If they were all even exponents, it would be y symmetry, y-axis symmetry. If they were all odd exponents, it would be origin symmetry, but we have neither in this case. So now we have to graph. Oh, the fun. Okay, now this, I'm actually glad I'm doing this because I wonder if I can make this bigger. Can I? I don't think I can make it too much bigger. Okay, well, that's too bad. Okay, I was looking for a setting where I could blow it up because it's actually not that easy for me to look at. It's kind of small. Okay, so first of all, now we can take all those things that we have deduced over here, right? That this thing goes down, it starts down to the left and it goes up to the right. So that means I'm starting down here in this third quadrant, right? And I'm going to go up to the x-axis. And I cross the x-axis, and I know from my previous results that I blast straight through the x-axis at all of my roots. And remember, my roots are 3, 1, and -1. So that means -1 is going to be the first one we hit. Okay, so we'll pick the polynomial tool right there. You notice it's all wiggly. It has a bunch of points. And we are going to start at the lowest root, which is -1. Okay, notice it's not doing anything. It's just a blue line straight across. But if I start moving things around, right now it's a line tool. So the next point that I come across here is not, I'm not going to be dealing with my next x-intercept. The y-intercept is at 3. So I know the point 0, 3 is a point on my graph, right? We found that already. Now, I have another x-intercept at 1. So I'm going to click that now. So that's pretty nice so far. We got all of that. And then the next one is going to be at 3. So we clock that right there. Now that should be our graph. Notice we actually needed at least one in-between point to graph this. Okay, it turned out to be our y-intercept, and that's y-intercept is usually a really easy point to find because all you have to do is plug in 0 for x. So it's typically that's the point that you use for your extra point. So let's see what we got here. So let's save that, and now we'll check our answer. Hey, it worked. Okay, so it may take a little bit of doing to get used to that line tool. Okay, but you will have a whole bunch of these things to work on. It'll be lots of fun. And basically what you have to do is just, you're deducing things. This isn't a hard, fast graph. This is a deduced graph, so you just have the major properties. It's basically a good sketch of the graph is what it is. So in any case, that's the introduction to graphing polynomials. We'll get a little more carried away with it in the next few things. But until then, until next time, keep your pencils and your wits sharp. Thank you.